In this video, we are going to go over the following question. How do you access volume AC stresses in a frequency response analysis when you're configuring MSc Nastran SOL 200 or an optimization or sensitivity analysis? So this can get a little complicated, so that's why I wanted to create this video. One thing you need to do before you start this, you need to confirm the item codes that you're going to be using. So here are some examples of what the item codes could look like. If you're working with C quad 4, you could be dealing with either element 144 or element 33. If you're dealing with C tria 3 elements also, that adds additional complexity like you see here. So here we have C tria 3. Now, let me explain why this could get a little complicated. So let's go here. Let me move this here. Let me start off with this element. Let's suppose that you wanted to constrain. Let's go look here. Suppose you had C quad 4, 144, and you wanted to constrain this item code. Item code 9 as an example. So for C quad 4, and we're talking about dynamics here, so we're dealing with either real, imaginary values for now. For those who are using magnitude and phase, it would be the same. So this also applies to magnitude and phase. Okay, so let's suppose we're dealing with dynamics, so we're dealing with real, imaginary, or magnitude phase values. For item code 9, element C quad 4 type 144, this would be the shear XY as Z1 value. Now, what if this is C quad 4 element 33? What would that look like? So we'll go ahead and flip through here. So 9, item code 9 would actually be a thickness value. It would be the Z2 fiber distance. So this would be the thickness from the midplane to the top of the P shell element, if you will, a C quad 4 element. So this wouldn't even be a stress value, it would be a thickness value. So what if we're dealing with C quad 3 or C tria 3? And I think it was element 74. So what would that look like? Let me close this and show you what that looks like. So here, if we'll look at this carefully, item code 9 would actually be shear XY as Z1. So shear, oh no, I'm making a mistake here. It's important to read this carefully. Right now I was incorrectly looking at C tria 6, item code 9, but we don't have C tria 6 elements. We have C tria 3 elements. And if we look here at the description, it says that the item codes are the same as C quad 4 33. So here back on the right, we'll copy this cell here. So you can see if you use different item codes, or if you use the same item code, you might get different values depending on which element you're working with. So here, if you have C tria 3 elements in your bulk data file, you want to use C quad 4 element 33 just so the item codes are consistent. So here, if you have C tria 3 elements, use C quad 4 element 33. Else, use C quad 4 144 or C quad 4 33. So you have some options available. So again, if you have C tria 3, you have to use C quad 4 element 33. Otherwise, you can use either C quad 4 144 or C quad 4 33. It's really up to you. So here, I'm going to assume you have C tria 3 elements. So this is what you want to do. Here are some examples of how you trigger C quad 4 element 33 and 144. Say you use the center option. Oh, I think I may have mixed up the options here. Corner. Oh no, this is right. So here, let's suppose you use one of these commands. Stress equals corner, or stress corner, stress byline equals all. The way you do this is as follows. You go to the bulk data file. You copy this here. So this would be the stress command. You could use center. You could use corner. You could leave it blank, or you could use byline. So that's what I'm referring to, the stress command. If you use, say, center, or you leave it blank, this is going to trigger C quad 4 element 33. So if you look here carefully, we'll go ahead and just look at one element for now. If you center or you leave it blank, you get stress outputs for each element, but they're only for the center of the element. Now, if you use the corner or the byline option, for one element, you get the values at the center and the corners of that element. So here I get corner 100, or corner 1, corner 2, corner 3, and 4. So this would be at grid 100, or node 100, node 101, node 201, and node 200. But then this conflicts with the C tria 3 element here. So here we have a C tria 3. Sorry, I think it was 74. The C tria 3 is only going to give you values at the center of the element. So here we have a conflict. If we pick item code 9, which I believe was this one, 5, 6, 7, 8, 9. I forget which one it was. I think it was this one. Let me look here. Item code 9, shear XY, right. So that would be this item code. So this is item code 9. But then for the C tria 3 element, item code 9 was actually this value, the fiber distance for Z2. So there's incompatibility with the item codes. On the other hand, if you use the center option, item code 9 would give us this. What is item code 9? Oh, right. Let's fix this. Let's look at the correct one. So here, let's suppose we select item code 7. So item code 7 here for C quad 433, what would that be? That would be shear XY at Z1. And this would be the real or magnitude value. And then it would be same for that. And then for C quad 144, what is item code 7? So here it would be normal Y at Z1. So you can see there is incompatibility here that we should always take into account. So here, item code 7. So this would be item code 7, the real value. And then here, item code 7 here would be the 0.0 for the triangular 3 element. So here, this example has a C tria 3, I believe. Let me try and find it. So that would be here at the very bottoms. So we have to use the center option. So what I'm going to do here for the stress, I'm going to use center. And then that's going to output values only at the center of the element. Now let's go ahead and look at what item codes we are going to be using today. So let's go ahead and look at this. C quad 4. Okay, so if we look at the von Mises stress equation, we need values for the X, the Y, and the shear. So we need values for the X, the Y, and the Z. Let me go ahead and delete some of those. Maybe we'll go ahead and delete these rows. So let's look at this. So for normal X at Z1, we want item code 3. So we'll say item code 3 for now. So this would give us the normal X at Z1, and then whatever happens for that happens for the other element too. And then we want the normal Y, so that would be item code 5. Normal Y at Z1. And then right now we're dealing with only the real values. and then we want item code 7, so that will give us shear xy at z1 rm. So we want these item codes for the real values so far, and then we want this for, say you want to do this for the imaginary values, so you would increment up a little, 4, 6, and 8. So these would be the imaginary. And then this would be for Z1 so far. What about Z2, which would be the other thickness? So this would be the bottom of the thickness and bottom of thickness. And this would be top of thickness, top of thickness. And we'll go ahead and just copy those item codes here. But they're going to be a little different because here, this would be at 10. And then 12, and then 14, and we'll repeat here 11, 13, and 15, and then here all these Z1s should be Z2, so we'll go ahead and update that. So now we know what item codes to use. So we'll go ahead and create our equations for the von Mises stress. So let me go ahead and do this. We'll call this response R1, R2, R3, or actually I forget what the name is. I think they're B1. Right, I think these are B1. Okay, so let's rename these. This is going to be B1, B2, B3, B4, B5, B6, B7, B8, B9, B10, B11, B12. So then what we're going to do is say that our equation is going to be as follows. So we're going to say the von Mises stress, Vm, this is going to be the square root of B1 squared minus B1 times B2 times B2 squared. And let's go ahead and see what's at the end of this, plus 3 times, let's see, that's going to be B3 squared close. So throughout this video, I may or may not get this equation right. So triple check this equation that I end up using. So square root of B1 squared minus B1 times B2 plus B2 squared plus 3 times B3 squared. And then we'll go ahead and do the same thing here. This time it's going to be B4 squared minus B4 times B5 plus B5 squared plus 3 times B6 squared. Now, I'm going to skip doing this for the top of the thickness Z2, but I'll leave it up to you to do it because this might actually make the video really, really long. So let me confirm I've done this right. So B4 squared minus B4 times B5 plus B5 squared plus 3 times B6 squared. Okay, so this looks okay. Let's go here and do this. Let's go out of this. Let's go to the optimization web app. Let's go ahead and select the bulk data file. And let's just go ahead and create a dummy variable for now. So any property here would be the dummy variable. We'll select a dummy objective. We'll say we want to minimize the mass. And now for the constraints, we'll go to equation constraints. In this table, step A, additional responses, let's go ahead and look for stress. And here, since this is a frequency response analysis, we're dealing with element stress. So let's go ahead and create 3 responses. So this is going to be P shell. And then let's go ahead and confirm our item codes here. So we want item code 3, 5, and 7. So item code 3, 5, and 7. So this is going to be normal X stress, normal Y stress, and shear XY stress. We want this for all the frequencies, so we'll leave it at that. And then we want this for maybe P shell 1 as an example. Okay, now in this equation table, let's go ahead and create one equation. Let's go ahead and type in that expression we had a moment ago. Here, we can just copy and paste that here. And there's a problem here. Let's go ahead and see if we can detect what our problem is. I believe the exponents should always have a decimal point. So we'll say to the 2, to the 2, and to the 2. Oh, that still didn't fix it. So let's see if we can figure out what our problem is. Oh, here, that's the problem. I forgot a decimal point here. And then we'll give us an upper bound of, I don't know, maybe 1 for now. So that's our first expression. So let's go to the next expression. So we'll go ahead and copy that here. And then we get a problem that the 3 doesn't have a decimal point. And then we get a problem that these responses do not exist. So we'll fix that in a moment. Let's give this an upper bound for now. And here we'll go ahead and create a few additional responses. So we'll click that 3 times. We'll display at most 10 rows. And here, let's go ahead and select P shell, and then here we'll do this for the imaginary values. So 4, 6, and 8. Let's confirm 4, 6, and 8. Okay. And then for P shell 1. And then when we do that, the error should have gone away. Okay, now let's see if this works. I suspect this might not work, but we'll see if it does. And then for now, we'll do a test run. So we'll say perform a sensitivity analysis. And we'll go ahead and click download values. Now, this may or may not work because I forget if the I forget if the exponents need a real number or a decimal point. So we'll do this. Let's just run this and see if it works. If we look here at the equation, the exponents have a decimal point, like in this example, 2.0, but here it's just 2. I don't know if this will work, but let's see if it does. Oh, it seems like it did work. Okay, good. So now let's look at the F06 file. And now, you know, one thing we should have probably done. Right, let's do this. Instead of doing this for every P shell entry, let's do this for just one element. Let's say we want this for element. Let's go ahead and see what the elements are in this example. Let's say we want to do this only for the first element, a C quad 4101. So we'll switch all of these to element. And we'll go ahead and make this a 101. Now, the reason I want to do this is because I want to confirm I did this properly. So let's go ahead and export this. We'll rename it working directory 1. I never like to work with spaces or parentheses in the file name, so I renamed it _1. We need to confirm our equation is correct. So if we look here, we get some data, and then I think there may have been an error. Okay, let's see what the error is. So we'll look for user fatal message, system fatal message. Oh, so we get a problem with one of the exponents. Okay, so I guess it did not like the exponent, which was odd. A moment ago, it worked just fine. Here, the exponents have decimal points. I'm assuming it doesn't like the decimal points, so let's go and remove that. Let's go ahead and space this out so it's more readable. So the only value that should have a decimal point is this 3.0. The exponents do not have those decimals, so let's zoom out and let's try this again. So let's go ahead and get our bulk data file here. Let's go ahead and rename this to. Let's go ahead and run this. And this time it should not have an error. Okay, that worked. Now let's go ahead and look inside the F06 file. You get this table called responses and design model. So I believe that should be here. And then, right, I think we only want the first three values. So here, let's go ahead and get the first three values. Notice that the first three values are for components 3, 5, and 7. So the stress in the X, the Y, and shear stress in the XY plane. So let's go ahead and copy this. And let's go ahead and maybe open a new sheet here. And let's use that von Mises stress equation that we had a moment ago. So the von Mises stress, that's going to be equal to the square root of sigma 1 squared minus the product of sigma 1 times sigma 2 plus sigma 2 squared plus 3 times sigma 1, 2 squared. We found a typo. Okay. Excel does not use the double asterisk, so I'll have to use this character, this caret, I believe it's called. Okay, so here a1 squared minus a1 times a2 plus a2 squared plus 3 times a3 squared. So here we get told that the von Mises stress is 852.83. And now if we look here at the F06 file, if we scroll down a little bit more, we get the retained DRESP2 responses, and we get the first response. Here we get 852.84, which is the same value that we got here in the spreadsheet here on the right. So this tells us we've correctly calculated the von Mises stress. This is a good way to double check if we've done this properly or not. Okay then, let me look at this and end it off. Okay, so far this was the so-called real value. What about R2? This equation, or these responses, a 9,000,001, I believe it is. These are for the real values. So let me highlight these rows. So these rows are the von Mises stress for real values. The next set of responses for 9,000,002, these are the von Mises stress values for the imaginary components at Z1, which would be the bottom of the thickness at Z1. Previously, I showed you the expressions to do this for the Z2 fiber, which would be the top of the thickness. So here it would be the square root of B7 squared minus B7 times B8 plus B8 squared plus 3 times B9 squared. Now for the 3, you want to make sure that there's a decimal point, and then that would be the expression you would use, and then you would repeat this for the next set of values. I didn't show you how to do that because it would just make the video too long, and I wanted to save some time. Now, so far, we've been dealing with real imaginary values. So if you look here, I don't think I have it, but I think it might be worth showing you how to do that. Let me go ahead and go back to the stress command, and let me say print. And let me rerun this. Now what print is going to do, it's going to say print the stress values to the F06 file. This is going to give you a lot more data, but here what I want to show you is the following. Here you can see that at the top of the table we get real / imaginary values. I forget what the command is. I think it might be this. Let's see if that's what the command is. Here, let me pause the video and double check. So the command is phase. So let me show you what that does. Let me copy this real quick. So this is stress, real. This could be imaginary. I think they use IMAG. And then here we're using this other option, phase. So what does the phase option look like? So let me delete this. Okay, now let's look at the F06 file and see what we have now. Let's go ahead and copy this. So before our values, these values here, these were real values. And then here, these would be the imaginary components. When we use the phase describer here in the stress command, we now get magnitude and phase components. So these would be the the magnitude values, and then these would be the phase values. Now, the implication is the following. Our responses are now different. So let's go and look at the responses here. So these responses would be either the magnitude values, and then the next ones would be the phase values. And when we look at our DRESP2 responses, we would get von Mises stress values for the magnitude component, and we would get von Mises stress values for the phase component. So that's one other thing I wanted to point out. How do you switch between real, imaginary, and magnitude and phase? So we're at the end of the video. Hopefully this video answered the question, how do you get von Mises stress values? This question came up because one of my viewers saw this. When you're dealing with only real values, you do get an item code for von Mises stress. So you would use item code 9 if you're dealing with SOL 101 or linear statics analysis. But when we start playing with frequency response analysis, you no longer have the von Mises stress component. But if you want to get a von Mises stress value, that's okay. You just have to go ahead and create some equations here in the web app. And then that's what we did here in these tables. Okay, that's pretty much we're at the end of the video. And as always, thank you for watching.